Welcome to Cooking 101, How to Make Spaghetti, featuring thermodynamics. The first step in cooking anything is to turn on the stove. We will be using ethanol as a fuel for the stove, which has a power output of 300 watts. How do we know this? Using the equation P equals Q over delta T and Q equals MC delta T, we can find this out. In the immersion heater lab we conducted prior, we calculated the power output of a given immersion heater. Assuming that this heater has the same power output as our stove, our data and calculations were slightly off from the actual power output, which was 300 watts. This resulted from the minor inaccuracies in our experiment from recording temperature and time. Next experiment, the heater combustion lab, we tested different alcohols to see which produced the least CO2 per mole burned and which had the highest enthalpy of combustion. Since this was an exothermic reaction, we used the heat generated from the alcohol to heat the water to find Q in the equation Q equals MC delta T. Our results showed that ethanol was the most efficient fuel to use. Now for step 2. Let's heat the water. Heat is a transfer of energy, and in this case, energy from the stove fueled by ethanol will enter the pot of water. This is exothermic for the stove as it is giving off heat, while it is endothermic for the water since it's taking in the heat. This is shown by the equation Qin equals negative Qout. When water reaches boiling point, which is 100 degrees Celsius, what happens? As a change in state, potential energy increases and liquid water changes to water vapor. As an increase in temperature, the temperature of the water increases by increasing the kinetic energy. Here's a graphical way to show an object when increasing temperature and changing state. With the steeper slopes, it shows that kinetic energy is increasing, therefore temperature is increasing. Remember, temperature is the average kinetic energy of an object. When temperature reaches the melting and boiling point, temperature stops increasing since potential energy is being increased to change the state of the object. The longer you boil the water, the less water will be in the pot. This is because of the first law of thermodynamics, which states that energy is not created or destroyed, but rather conserved through changes of state. With latent heat of vaporization and fusion, potential energy just increases or decreases to change the state of the object, thus preserving its energy. Step 3. Now place in the raw spaghetti noodles. Due to the second law of thermodynamics, which states that heat spontaneously moves from a hot object to a colder object, energy from the hot water will move towards the colder pasta noodles. This heat flow will continue until the pasta and water reach thermal equilibrium. After waiting a few minutes, let's see what happens. The noodles reach thermal equilibrium with the water. Keep in mind from the zeroth law of thermodynamics, two objects are in thermal equilibrium when they are both in thermal equilibrium with another object, for instance, a thermometer. This process, where does enthalpy come in? Remember Hess's law with enthalpy, which is the sum of enthalpy of formation of products minus the sum of enthalpy of formation of reactants to give the enthalpy of the reaction. The heat added will allow the enthalpy to denature the proteins and enzymes in the pasta noodles. It is also responsible for breaking intermolecular forces by changing the bond energy holding the molecules. Step 4. Now it's time to take out the noodles. Don't let the noodles sit out too long or else they'll cool down by giving heat to the colder plate and surroundings to reach thermal equilibrium. Cough, exothermic. But don't worry, due to the third law of thermodynamics, no object will ever reach absolute zero since there is motion even at the atomic level. Place the noodles in the fridge and it won't be 0 degrees Kelvin. You notice I've mentioned endothermic and exothermic a lot in this tutorial. It's because it's an important concept to know. In breaking and forming bonds, when energy to form bonds is greater than energy to break bonds, it is exothermic and vice versa. In enthalpy of formation using Hess's law, when change in enthalpy is negative, it is exothermic and vice versa as well. Now, your spaghetti is finished. But wait, you need flavor, right? If you want flavor, be like Sape and add a pinch of salt. Fun fact, salt bay is increasing the entropy of the system. By adding salt, he is increasing the number of particles in the closed space, creating more disorder. Entropy is denoted by delta S with a negative, indicating decreasing disorder and vice versa. It correlates with Gibbs free energy, where a negative S indicates a positive G, which is non-spontaneous and vice versa. To sum up Gibbs free energy, this graph shows the spontaneity of different reactions when entropy and enthalpy change. The equation delta G equals delta H minus T times delta S also shows the spontaneity. A negative G indicates the reaction is spontaneous and vice versa. Enough talking now. Now go enjoy your spaghetti, which hopefully looks like that. You're welcome.